Welcome to the magic of trig substitution. In this video, we're going to spend some time filling in this giant chart of instructions. And then along the way, we're going to do this example, which is the integral of the root of 4 minus x squared. All right, so the types of integrals that trig substitution will apply to have generally these things in them. So the a squared in each of these items in this first column, this is just going to be a number, right? So in our first example, we have 4 minus x squared. This might be 9 plus x squared. The only reason we write a squared instead of just like number or a or something in these spots is because it's always going to be a positive number the way this is written. And then in this category over here, we'll refer to just plain a, which is the square root of the number you're looking at here. Okay, so we'll fill in the first row of this chart kind of with instructions, and then we'll see how they apply to that first example. All right, so in your integrand, if you see the root of something minus x squared, your move is going to be to plug in x equals a sine theta. So this a right here is just the square root of whatever number is right there. Theta is a new variable. So what we're doing is sort of a backwards substitution. Instead of subbing in a u that stands for a whole piece of the integrand, we're sort of doing the opposite, where just x comes out and a bunch of new stuff comes in. Right, so if this is what x equals, then dx would just be the derivative of a sine theta, which is a cosine theta. I'm going to put a d theta at the end. That d theta is something that you might want to skip if you don't like it. This substitution also comes with some constraints on what theta is. So this substitution x equals a sine theta is for theta in the interval minus pi over 2 to positive pi over 2. This is the right half of the unit circle. This is all the angles from here all the way up to here. There's a few different perspectives you could take on why this restriction needs to be made. One way to see it is so that x equals a sine theta is a one-to-one relationship. You could also see this as the range of arc sine. That's the first place that this restriction comes in. But anyways, don't stress it too much. Anytime you make this substitution, you just write this underneath it, and that'll never change for the sine version. Okay, so you'll make this substitution and plug in all your stuff into your integrand, and it makes your integrand look significantly worse than how you started. Okay, and then the next category here is factor out the a squared and then simplify with. So when you put a sine theta in for x here, you get a squared minus a squared sine squared. And then a squared is in both terms, so you can pull it out. And what you're left with is 1 minus sine squared. 1 minus sine squared. And we rigged this up on purpose with that sine substitution because we have an identity sine squared plus cosine squared equals 1. So we know that 1 minus sine squared would be cosine squared. So we'll replace this with this. So you just have the root of cosine squared. And that helps things simplify as you go. Okay, and then this last column here is maybe also this. So this substitution always definitely happens. It's kind of the crux of the whole thing. This usually comes with it, but isn't necessarily used in the problem. So over here, we said this, it would be under a square root here. So you end up with the square root of cosine squared as part of your integrand. And we want to say that the square root and the square perfectly cancel here, but what's actually happening is an absolute value. Because if cosine of theta was a negative number, and then you square and then square root it, you've now lost the negative sign along the way. So technically it's absolute value. But this is the magic of this domain restriction here. So this was here to keep this one-to-one, but now we're thinking, oh, well, theta is only an angle on the right half of the unit circle. And for all of those angles, the cosine is a positive number, right? Because it's the x value of these points. All the negative cosine values are on the left side. So we can actually go one farther and say what we were hoping to be able to say, which is that root of cosine squared in this particular case equals cosine theta. All right, This looks bad, which is why we're doing a video instead of reading stuff in the book. So before we finish the rest of this chart, I want to show you what these steps look like in an actual example. So if we start with 4 minus x squared in the root, you can see that it matches this first row where the a, technically a is 2, right? Because a squared is the 4. Okay, so the instructions here say sub in x equals 2 sine theta. We're going to compute the dx that goes with it. Dx would be 2 cosine theta, d theta. And then we'll throw in this restriction, minus pi over 2 to positive pi over 2. Again, you don't have to overthink this. It's just this is the restriction that always comes with that substitution. Okay, so I'm going to go one step here. Square root of 4 minus. In this particular example, the only x in the integrand was right here. So this is the only place where I have to put 2 sine theta. We will eventually see examples where there's other x's running around, right? There's like an x squared out front. In those cases, everywhere there's an x, this 2 sine theta shows up. But for us, it's just the 1 right now. And that was x squared, so it's 2 sine theta squared. And then this dx comes out, 2 cosine theta d theta comes in. Okay, so we have done these first 2 columns of instruction. Now we're going to factor out the a squared, which is 4, and simplify with this identity. And it's all going to work a lot better than it looks like it's going to work here. So the first thing I'll do is say, well, 2 sine theta all squared is 2 squared sine squared. So we could call this 4 minus 4 sine squared theta. I did my root a little too long. Shorten that. Oop. All right, and then 2 cosine theta still on the outside. Okay, so we're going to factor out the a squared, which in this case is 4. And now we have the square root of the product of 2 things. So really I can make this square root of 4 times the square root of all the rest of this and just make it its own separate root. And I say, oh, well, the square root of 4 is just 2. Okay. I'm also going to do this substitution in this step. So I say, okay, 1 minus sine squared is right there under the root. I'm going to replace it with cosine squared. Okay, let's see what we have. That's 2 times the square root of that cosine squared that just showed up, and then the 2 cosine theta that's been there the whole time from the dx. This 2 and this 2 I can combine into a 4. And now this square root of cosine squared is this predicted identity down here. So we can say, all right, well, technically that's the absolute value of cosine theta. But in this particular case, because of this restriction here, we can replace that with just plain cosine theta. We don't have to worry about those absolute values, which is good. So I have a cosine here and a cosine here. That gives me cosine squared with that 4. Okay, so now we have simplified our integrand as much as we possibly can, and we need to integrate. Cosine squared doesn't have its own memorized antiderivative rule, but it is one that we've seen before. You can do this either using the double angle identities or as a wraparound integral by parts. That times 4 will carry down. If you do it as the wraparound integral with by parts, you get 1/2 times sine theta cosine theta plus theta. And then, of course, we throw in the plus c. 4 times 1/2 we can call 2. x was 2 sine theta. So right here, we can replace this with x divided by 2. And then these two guys, we are going to talk about in class together. So our goal is to get this final answer into something in terms of x instead of theta, now that we've actually integrated. This gets a little extra dicey. So I'm going to leave these for a conversation in class, but that would be our very last step here. So we'll come back and finish this chart now that we've seen this in action. So we did the prescribed substitution, subbed everything in, factored out the number in common. This number should always be in both spots because we made that happen. And then once we do that, we say, oh, look, I have a trig identity ready to roll for what's left. That'll always be the case for all three of these. And then simplify, integrate, and then replace. And we'll continue that conversation later. So let's come back to this chart and finish it off. When you see addition between the number and x squared, you're going to make a different substitution because you'll get 1 plus the trig function squared. So we need to pick a trig function that has an identity that looks like that. Our choice is going to be x equals a tan theta. That would make the dx a secant squared theta d theta. That's just tan's derivative. And then the restriction on theta is theta is in minus pi over 2 to positive pi over 2. But now with parentheses instead of brackets, just because that's the range of arctan. So that's the same angles. We're just excluding the edges here because there's no tan there. Okay, so in that case, once you factor out the number, you get 1 plus tan squared. And we have an identity that tells us that's equal to secant squared. Very similar to this one. That means we'll end up very likely with square root of secant squared, which technically is just the absolute value of secant. But if we're on the right half of the unit circle, cosine is positive, which means so is secant. And we can just turn that into regular secant. The third one goes very similarly. If you have x squared minus the number here, once you factor out that number, you're going to have trig squared minus 1. So we need to put in a trig function that has an identity that looks like that, which is secant. So we have x equals a secant theta. That would make the dx a secant theta tan theta. This is the most difficult range. It's a little messy, but it's always the same. So anytime you make this substitution, this is the same restriction. Theta will be in bracket 0 to pi over 2 parenthesis, union bracket pi to 3 pi over 2. Let's take a peek at what that looks like. Okay, so 0 to pi over 2 is the first quadrant here. And then we'll go pi to 3 pi over 2, which is the third quadrant here. This isn't one that we tend to know off the top of our heads, but this will be the range of arc secant. So it just keeps this a one-to-one relationship. Okay, so once you make the substitution, you put everything in, you factor out the number in common, we get secant squared minus 1. This is actually just a rearrangement of the identity above it. If you subtract 1 from both sides, this left-hand side becomes tangent squared. So now you end up with, under the root, tangent squared. So more likely than not, this will come up as part of your integrand. Technically, it simplifies only to the absolute value of tangent. But then if we look at this restriction on theta, we say, oh, well, in the first and third quadrant, tangent is positive in both these places, right? Because sine and cosine are both positive here, and they're both negative here, so tangent comes out positive. So once again, we get to simplify it all the way down to tangent theta.